So here we go with the orbital shapes. The size of the orbital, and this is going back to that probability definition, is the area that will include the volume, I should say, that will include 90% of the probability of finding an electron. So it's not going to be on the surface of these shapes. It's going to be somewhere inside the shapes. Now, will it be in the nucleus? Probably not. So inside this volume, excluding the nucleus, most likely. Okay? As the principal quantum number gets bigger, these orbitals take the same size. They just grow. So the s orbital is a sphere. 1s is pretty small. 2s is bigger. 3s is bigger. 4s is bigger. But it's a sphere centered on the nucleus. So not that big of a deal. They just get bigger as they go. And if it helps you to remember s sphere, remember that. The p orbital, remember there are 3 orbitals for p. Each has 2 lobes. There's no 1p. P starts at level 2, and that's just because of the way the equation works out when we solve the equation. So here are those 3 p orbitals. Now, they're not separate like this. In a real atom, they'd all be mushed together in the same thing. So you'd see 6 lobes all kind of protruding from the nucleus. But this is p. The one along the x-axis is called px. The one on the y-axis is py. The one along the z-axis is pz. You don't need to know those. But remember, these are for L, it would be L equals 1, because that's P. And then it'd be -1, 0, and +1 for these 3 orbitals. For us, it doesn't matter which one is -1, which one is 0, which one's 1, because they're symmetrical in every direction. Just pick one of them to be -1, one of them is 0, one of them is +1. We can get a little more complex. We can get to the third level. Third level has 3s, which is just a bigger sphere, 3p, which is the exact same shapes, the px, py, and pz, along those same axes, but bigger. But then we also add in the d sublevel. And there are 5 orbitals in the d sublevel, 5 regions in which the electron is most likely to be found. And you can see them here. We don't care what they're called, the dxy, dxz, dyz. We don't care about that stuff. But there are 5 of them. You can see their shapes. 3 of them are in between axes, 1 of them is on the axes, and the last one is the exploding donut. Well, that's what I call it. It's not the official name. But these are, again, -2, -1, 0, +1, and +2. These are the shapes that we are likely to find an electron with a 90% chance. You want really complicated? Here's the F. We've got the double exploding donut. We've got flowers of all shapes and sizes. There are 7 f orbitals. They get very complicated. You'll notice these look like they were done by a computer because really that's the only way we have to solve these, to figure out what the shapes are. Most of the time, the f orbitals aren't involved in any kind of bonding. And really, the d orbitals aren't involved in bonding very frequently either. So S and P are usually the ones we're most concerned about because those are the ones that are usually involved in a reaction. It's not until you get into more complicated chemistry later in college that you're going to have to worry about D bonding or F bonding. In terms of energy, all orbitals that have the same principal quantum number n have the same energy. Now there's a little bit of variation in there, but we're just going to say that everything at level 1 is the same. Everything at level 2, all of the p orbitals at level 2 are the same. All of the d orbitals at level 3 are the same, and the p orbitals at level 3 are the same. But the p and the d aren't equal to each other. Okay? All of the orbitals in the same one there have equal energy. The lowest energy state we defined last year is the ground state, and as electrons absorb energy and they move to farther away from the nucleus orbitals. Remember, they jump out. Well, they don't really jump out. They jump to a bigger orbital. That means that the area in which we're likely to find them increases. And that just makes sense. If you give a little kid a bunch of sugar, you're more likely to find, you have to widen your search area to find them on the playground, right? Because they're going to be running all over the place. Same thing with an electron. You give an electron more energy, the area in which you're likely to find it grows because it's more energetic. Now it's going to stay in the same basic shape by solving that equation, but it's just in a bigger shape. So if it jumps from a 2p to a 3p, it's going to be in a bigger shape. If it jumps from a 2p to a 4d, it's going to be bigger and in a different volume. So things can get really, really complicated. But we're going to simplify it in here. When an electron absorbs energy, it jumps to an excited state, which is a higher energy or higher N level. And then when it loses the energy, it goes back to a lower N level, lower energy level, eventually making it all the way back down to the ground state, which is the lowest possible, the closest it can possibly be to the nucleus. The joke at the bottom of the slide about forbidden transitions just talks about where an electron can jump from one level to another. Any level it can jump to is an allowed transition. If an electron tried to jump below its ground state, for example, that would be a forbidden transition. It's kind of an esoteric joke, I know, but it's a little funny in context.